Hi everyone, welcome to the worksheet 6 video key. Okay, so the beginning of worksheet 6 asked us to do some definitions, right? So I wrote them down in advance here. Torsional strain is defined, and you can, have slightly different definition as long as it means the same thing. But I defined it as the difference in energy between staggered and eclipsed conformations. So for example, right, if you were looking at ethane, ethane might have a staggered conformation that has all of the hydrogens drawn like this in a Newman projection, right? And because there's a 60-degree torsional angle, right, this would be considered completely staggered. And if we did a 60-degree rotation, right, so we'll do 60-degree rotation, and we can rotate either the front carbon or the back carbon, it doesn't matter. And I think the book typically did a front carbon rotation, but I'll show you a back carbon rotation. And as well, you could rotate clockwise or counterclockwise, right? So there's any sort of 60-degree rotation would be okay here. But let's imagine that we're going to rotate the back carbon. That means that this hydrogen would move 60 degrees this way if we're going clockwise. And then this hydrogen would move 60 degrees this way, and this one would move 60 degrees over here, and we would have an entirely eclipsed conformation. If I'm rotating the back carbon, then I'll just draw the front carbon with the hydrogens in the same place. And then if I want to draw an eclipsed conformation, I can kind of just try to do it as close to behind the front groups as possible. Right, so we might do something like this. And again, it doesn't have to be perfect. Usually they're slightly askew, so you can actually see what's behind there, even though the intention is that they're directly behind. And so something like this would be a eclipsed conformation, right? So it's the difference in energy between staggered and eclipsed. And this, again, is just an example using ethane. And remember that each eclipsing two hydrogens costs 4 kilojoules per mole, right? So the energy cost, also known as the energy barrier, was about 12 kilojoules per mole for this, which later on we're going to be graphing and using kilocalories, right? So it's important to know that roughly 1 kilojoule is approximately 0.24 kilocalories. Right? So 12 kilojoules per mole would be approximately equal to about 2.87, right? Or you might say approximately equal to 3 kilocalories. So that will be useful for when we are doing graphing, which is a little bit farther down on the activity. Okay, let's talk about steric strain, though. Okay, so make a little note here that we're kind of giving an example of torsional strain. And then we'll talk about steric strain. So the steric strain I defined as the energy cost associated with non-bonded interactions of atoms or groups of atoms that are in close proximity to each other. So you may have run across the idea of a gauche interaction, and that is a type of steric strain. So let's look at steric strain, and I'll give you a couple of examples just because we are going to be seeing more examples of steric strain a little bit further on in chapter 4. So for example, let's do the gauche interaction. So if we look at the staggered conformation of butane, right, where we have we're going to look down the central carbon-carbon bond, we'll have two methyl groups, right? And at one point, they might be sort of right next to one another. And in that case, even though this is a fully staggered conformation, which means that it doesn't have any torsional strain, it is also considered a gauche conformation, which does have what's called steric strain. And that's because the two methyl groups, even though it looks like they're small, because I just wrote CH3, remember this is a carbon attached to three hydrogens. So the one that's sort of pointing over here is going to be running into the hydrogen that's pointing this direction from the other methyl group. These are actually pretty close together. And if you look at a more space model, you can actually see that. Right? So this is an example of a steric strain because these groups of atoms, which are methyl groups, they're not attached to the same, they're not attached to each other, right? They're actually attached to adjacent carbons. And so, and they, in this conformation, they get rather close together. So we call that a steric strain. Because again, those electron groups will repel one another. So it costs some energy to get it into that conformation. Right? And how much does it cost? Well, the book talks about 3.8 kilojoules per mole for a gauche conformation compared to the anti-conformation that's also staggered. And that would be approximately equal to about 0.91 kilocalories. And again, this will be helpful, right, when we start to do that graphing later on. Okay, here's a totally non-related example of a steric strain that will sort of lead you into the next part of chapter 4. So what we'll end up seeing later on is what is called, so now we're going to be looking at conformations of cyclohexane, which is a 6-member ring with carbons. And in one conformation, they end up with what's called a boat conformation. And again, this is of cyclohexane. We haven't talked about that yet in lecture, but you'll see it very soon. And a steric interaction here is that there's actually two hydrogens on cyclohexane on each of these carbons. And in this boat conformation, those two hydrogens, even though they're only hydrogen atoms, they actually get rather close to one another. And that is considered a steric strain. Notice how the hydrogens are not attached to one another. They're actually pretty far apart, right? Not even attached to adjacent carbons. But because of the particular conformation, they get pretty close to each other. And so there exhibits the steric strain for that. And so that's just a little preview of what's coming up soon. Okay, those are a couple of examples of that. And then what we want to do is talk about angle strain. So I wrote that the definition of angle strain is if the angle between two bonds in an X carbon Y system is less than the optimum value, for example, less than 109.5 degrees in a tetrahedral carbon or tetrahedral center, there is a destabilization due to the electrostatic repulsion of the electrons in the bonds. Okay, so that's a lot of words, right? But it's always good to like visualize an example of a steric strain, sorry, an angle strain. Because that really helps us see sort of the difference in what exactly are we talking about with these different types of strain. So another example that we will come upon soon is actually cyclopropane. So cyclopropane is a 3-membered ring made up of 3 carbons that are attached. And if you think about cyclopropane, right, we have a carbon, and each one of these has 2 hydrogens attached to it, as well as the 2 bonds that it's making to the other carbon. right? And so each one of these carbons, right, is sp3. So it has an ideal bond angle, of course, of 109.5 degrees. But let's look at what the actual bond angle is, right? For example, for this carbon, 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 right? So if we're looking at this as the central carbon, right? And this is the angle of, let's go label these with C1 to C3. So we're looking at the angle from C1, C2 to C3, right? And you might know that that is going to be 60 degrees, right? Because they all are going to add up to 180 in a triangle. So this actual angle is, as drawn, it looks like it's 60 degrees. Now what you're going to learn next time is that the bond, the angle, or that the atoms actually pucker, so they're not exactly, they sort of get a little bit of a larger angle to 60 degrees. But they, are fairly constrained by the fact that they're in a ring. So they're definitely a lot less than 109.5 degrees. So that would be considered, a significant amount of angle strain. Ideally, it would be 109.5, but it's somewhere close to 60. And again, what I was talking about with that puckered nature, right, is I draw these in. What will actually happen here with the orbitals is that they'll go out a little bit, as opposed to kind of following exactly a line between those two. So they can sort of have like a ideal line. They will, in all cases here, they'll go out a little. And so what happens is they give up a little bit of overlapped area, right? Because of course, if you had head-to-head overlap, there would be maximal overlapped area, which makes for a stronger bond. But they're giving that up in order to get a slightly larger angle, right, between all of the carbon-carbon bonds here. So, in all cases, it's sort of, we say pucker out. I'm sorry, that should be a little bigger here. Not very good. You get the idea. They're puckered out a little bit compared to sort of following a straight line. Anyway, so it's not exactly 60 degrees. They gain a little bit in angle by puckering out, right? But they lose a little bit in bond strength. So it's sort of a balancing act for stability. But this would be an example of angle strain, right? Kind of an extreme example of angle strain, because the angle is deviating significantly from the ideal angle for a tetrahedral carbon. Okay, so those are some examples that hopefully help you understand the difference between those different types of strain, which just refers to electronic energy differences. Now we're going to start working on drawing a graph of some conformations of ethane. And look at, if you notice, it's so the numbers that you get from the book in kilojoules, you'll just need to convert to kilocalories so that you can match the graph. There isn't a whole lot of space in this graph. So what I'm thinking about doing in order to answer this question is to draw all the conformations sort of on a separate sheet of paper and then like label them A, B, C, D, E, etc. And then put together the graph using the letters instead of the actual conformations. But you can draw really small, you can possibly draw them on the graph as well. I'm just not able to draw anything very small, typically. Okay, so again, we are going to be looking at conformations of ethane in this first one. And that means that we're going to look down the carbon-carbon bond. for example, if I draw a carbon-carbon bond, I could draw the hydrogens attached. And it doesn't matter if you put the dash or the wedge on either side here. Just as long as you know that this one's really coming out and that one's going back. We have to draw them on one side or the other, but like if I had made this one the dash and this the wedge, that would have been fine as well. And over here, put in those. So we're basically just going to be placing our eyeball over here and looking down this carbon-carbon bond, where the C1 is going to be the front carbon and C2 will be the back carbon. And of course, if we were just asked to draw what we see, right, then we would come over here and draw a Newman projection of what we see. And then again, C1 is this dot, right, and C2 is represented by the circle. So we would put the hydrogen pointed up. That would be this one. And then we have the one sort of going down and to the left and down and to the right. So from our perspective, if it's on a wedge, that would be down and to the left. I think that would be this one. So that's the wedged hydrogen. This one's coming out at you. So if you were looking this way, it would be on your right over here. Right? And if you want to, you can even kind of label the hydrogens. You can see like exactly where they are. So for example, I could label these like A, B, C, and F. Just so it's really clear exactly where they're going over here. So this would be HA, and this is HB and HC. Hopefully you can visualize that as well. And then on the back carbon here, which is represented by the circle, we've got HD, right, that's pointed straight down. And then we have the two that are off to the left and right as well. Right? And from this person's perspective, as they're looking this direction, this would sort of be up and to the left, and then HE is up and to the right. Go ahead and label those. FE. Okay. So this is, of course, a staggered conformation, right? But in order to be able to do this graph, we need to kind of highlight a couple of these hydrogens and ignore the rest. And then what it wants us to do really is start at 0 degrees. Of course, you could start anywhere on the graph, but to my mind, we start on the left here at 0 degrees. And if we have a 0 degree dihedral angle, that means that we start with an eclipsed conformation, right? Because remember that this is a 60 degree, right, angle between, for example, HA and HE. But we want to start with a 0 degree angle, which would be whatever hydrogens that we sort of start with or focus on, they will be 0 degrees away from each other. So they're starting in an eclipsed conformation. Okay, so what I want to do here then is draw out conformation starting with 0 degrees. Right? And we're going to highlight a couple of the hydrogens in particular. I'm just going to draw a starting point for a Newman projection. And then I'm going to draw in the front hydrogens. And you could either do them sort of up and down, or down and up like this. Either one is fine, and it really would not matter. But I'm just going to go sort of here, here, and here as a starting point. And then, of course, we're going to be drawing an eclipse conformation. But I'm also going to draw the ones that are behind it. And then I said I wanted to focus specifically on 2 hydrogens that are going to be 0 degrees apart from one another. So we'll draw these in red, the one on the front and the one on the back carbon. So we're kind of focused on those. And then these other ones will just be ones that we are not highlighting or focusing on. Right? So this is going to be the 0 degrees, right? Because again, those hydrogens have a 0-degree torsional angle since they're eclipsed. And then we're going to do a rotation of 60 degrees, and we're going to keep rotating 60 degrees, right? So that we have a Newman projection for every single one of these degrees that is highlighted on the graph. So we can choose now whether we want to rotate the front carbon or rotate the back carbon. That doesn't matter, right? If you did the front or the back, it wouldn't matter. I am going to choose the back. And by the way, I'm just going to kind of go a little bit lower than this because remember that eclipse is going to be the high energy conformation, right? So it's going to be higher in energy than a staggered conformation. I'm just going to kind of go a little bit lower just so that it kind of mirrors like an energy diagram. And then we will 60 degrees, right? And I said I was going to rotate, I think I said that I'm going to rotate the back carbon. So that means I'm going to leave the front carbon exactly how it is. And then I'm just going to rotate this back carbon 60 degrees clockwise. For me, it just makes sense to do it clockwise, but of course you could do counterclockwise as well. That would not matter. And what I'm doing here. So if I did a 60-degree clockwise, that is going to rotate over here. So now we have those, right, 60 degrees apart. Those two red hydrogens specifically. And now we're going to just keep rotating that black carbon 60 degrees at a time. So that we'll go behind this hydrogen, right? And then keep moving around. So we'll draw that next eclipsed conformation. So again, I'm rotating the back carbon. So I'm going to go ahead and, oh, I did not draw eclipsed conformation. So many things to think about. I'm messing this up. Okay, so trying to draw an eclipsed conformation, right? And draw that front carbon exactly like it was. And then if this rotates 60 degrees, right, it will be behind this blue hydrogen over here. We'll have blue hydrogen on the back of those two positions as well. So now we're at, right, the red hydrogens are 120 degrees apart from one another. And we're just going to keep going. Right now we're at 180 degrees. We'll be at a staggered conformation. And again, that front carbon is staying exactly where it is. So I'll go ahead and draw that in. And then the back carbon is rotating again to a staggered conformation. So we'll draw those in. That red hydrogen is now moved opposite, right? The red hydrogen on the front carbon. And so now this is those two red hydrogens are 180 degrees apart. And we can just keep going with that, right? We can move it on up to 240 degrees. Drawing that front carbon again in the same, and then we will be at a eclipsed conformation. That red hydrogen will move over here, and then the other two are blue. Right, so now measuring in this direction, right, that would be 240 degrees. So I'm just kind of starting out by drawing in a generic staggered and eclipsed conformation for the 300 degrees and the 300 degrees. So we have red hydrogens here, and then they go back to full 360 degrees from the starting point, so they're back to the original position and eclipsed again. Add in all these other hydrogens. Okay, and so what we can do here is just put this onto an relative energy scale, right? So we're going from, again, the difference in energy between the eclipsed and the staggered conformations is 12 kilojoules per mole, which was about slightly less than 3 kilocalories per mole, right? So if we're trying to put in relative energy levels, we'll kind of do, right, slightly below 3 for the 0 degrees and eclipsed conformation, going down to 0 when it's fully staggered, and then moving back up here to that same energy level at 120. And we're just basically rotating back and forth between those. So sort of put those in, and then the idea is to just draw a little like cosine or sine curve, right? Wave essentially between those. You can do your best. Maybe I'll try it in pencil first in case it looks horrible. But the idea would be to sort of come down here and back up, energy wise, and back down. All right. Obviously, we're not all artists, but we try to do the best we can there. And this would be, you can think, you could number this or however you want to do it, right? We'll go with, call this A, B, C, D, E, F, and G. Right? So then I can just kind of come over here and label those points. Just wasn't at all confident that I could put all of this right onto that graph along with this wave. Okay, so moving on then to butane. And it doesn't say so, but it probably wants us to look down that center carbon-carbon bond. It's going to be a little more challenging just because there's more energy levels to consider here for butane. But we can do it sort of the same way. We can look at all of the different Newman projections separately and then label them and then put them onto the graph. Okay, so I'm actually just gonna probably get rid of that for now, just so we can have more room. So let's see. So again, butane, let's kind of imagine what we're doing, what we're looking at first. So we are looking at 4 carbons in a row. And then we want to sort of label them. We're going to label these last 2 methyls. And then we're going to call this C1 and this C2. Again, sort of the front carbon and the back carbon. And then we can add in our hydrogens that are on a dash and a wedge. Okay, and then we can place our eyeball sort of either, again, to look down or up. But if I had wanted to look up, I should have labeled this C1, right, and that C2. C1 will always be the front carbon. Again, I'll just kind of, just like I did before, put my eyeball over here to look down that carbon-carbon bond. So what this is actually going to get us is 180 degrees apart for these 2 methyl groups. You can go ahead and draw that in. But that's actually not going to be our starting point of 0 degrees. So we can do those. We'll go ahead and draw what we see here, right? Just so that makes sense to us. And this is going to be in a staggered conformation with these methyls pointed straight down and pointed straight up on the back carbon. And if I want to, again, I can label these, right? So it's sort of A, B, and C, and D, just so that when I draw in the hydrogens over here, I can label them. And that will help you visualize in case you're looking at an example where one of the groups isn't a hydrogen, and you would need to differentiate exactly where it is. So if we have the person is looking this direction, it's sort of up and to the left is HA, and coming out of the page and to our right is HB. In there. And then from this person's perspective, again, right, pointed back down into the page, going to the left would be D, and go to the right is C. Okay, so this actually corresponds to, if we're looking at the two methyl groups, right, this would be what we want to draw for 180 degrees, which means in order to start at 0, we actually want these two methyl groups to be eclipsed. Right? So the way to look at that is you could even think of drawing it where the two methyl groups are going to be both pointed down with respect to the observer. Or another way to think of it is we call these two groups are anti-coplanar because they're in the same plane, or the y plane, right? So they're coplanar, and they're opposite, so we say this is anti. So this is, sometimes you'll see this referred to as anti-coplanar, right? Methyl groups. And then this would be the syn coplanar because they're going to be again in the same plane, right? But on the same side as opposed to on opposite sides, which is meant when they say anti. Again, let me draw my little eyeball up here, down at C1, C2 bond. And we'll draw our generic circle and our dot, right? Start our Newman projection. And we can see that we really didn't change anything about the front carbon from the top to the bottom. So I'll go ahead and draw that in exactly as I did up above. We have our methyl, and then HA and HB. Circle that so you can see that we're focused on that. And then as we look down here, what we did, right, is we essentially, it's kind of like rotating this 180 degrees or flipping it over, right? And again, this ability to visualize can be really tricky for students at first. So what you can do is you can make a model, right, to help you. So hopefully you have your model kit. You can build butene and then try to rotate the center carbon-carbon bond between the anti-coplanar and syn-coplanar conformations. So you can see exactly what it looks like when we sort of take this and rotate it 180 degrees or flip it over like a pancake. So what happens is, right, if I take something that's pointed out at me and I flip it over, then it's going to be pointed back. And the same thing is also true if it was pointed back and I flip it 180 degrees, it will be coming out at me. When I label these, right, I should label this. What was coming out when you flip it over is now pointed back. So this is now HC, and this is HG. Okay, and in looking at it this way, we're actually right now at a totally eclipsed conformation. Right, so I'm going to draw in those groups that are behind the front carbon groups. And then the second methyl, right, is here. Then I can circle that. Right? And then the hydrogens are here as well. Behind, you can see that HC is entirely eclipsed by HA. And HD is eclipsed by HB, right? So this would be the 0 degrees, right, apart for those two methyl groups. So notice that anticoplanar is actually a staggered conformation, and synproplanar is an eclipsed conformation. Okay, so again, we want to start with 0, right? If we're working from left to right on the graph. So we will go ahead and start with this conformation. So I'll just redraw it over here. And by the way, let's think about like energy-wise, right? Where should we kind of draw this? Should we draw this higher energy or lower energy? Well, right now we have the two methyls eclipsed, and that's going to be the highest energy or the least stable conformation possible. So that's definitely going to be the highest energy level. I'm going to try to sort of draw it starting from up high. So we'll do, just going to copy this. And again, I'm going to drop the A, B, and C and just focus on the two methyls and their relationship to one another. Just draw in hydrogens and we'll make the methyls a different color just so that they're really, we can, focus our eye on those two, right? And this is going to be our 0 degrees and our highest energy level. And we can kind of think about exactly how many kilocalories difference there is at the end by doing the kilojoule to kilocalorie conversion. So next, again, we want to either rotate the front carbon or the back carbon 60 degrees. And so what we can do is just focus on one. Just to be consistent with how we did ethane, we'll rotate the back carbon clockwise 60 degrees. Right? So we're going to come down here in energy because, of course, we're going to get to a staggered conformation. And I'm going to go ahead and draw in that front carbon because we decided we're going to rotate the back carbon, which means that the front carbon doesn't change. Right, and now we're going to get to a staggered conformation. So I'll draw my 3 lines here that represent a staggered conformation. And then we talked about how the methyl group, we're going to rotate clockwise 60 degrees. We'll end up over here, and we'll have 2 hydrogens at this position. So this is 60 degrees. But notice that these are gauche. So it's not going to be the lowest energy level for a staggered conformation possible. This is a little bit higher in energy because of the steric interaction between those 2 methyl groups, right? So we will keep that in mind. And then next, we're going to continue rotating that back carbon, again, 60 degrees. So we'll get to another eclipsed conformation. And we want to think about it energy-wise, right? Is it going to be higher or lower in energy than our initial eclipsed conformation? In this eclipsed conformation, the 2 methyls were eclipsed. So that's actually the highest energy conformation possible. Once we rotate this methyl 60 degrees, we'll have 2 methyl on hydrogen eclipsing interactions, which doesn't cost as much energy as a methyl on methyl. So it's going to be slightly lower in energy, but still high energy because it's an eclipsed conformation. I'm just going to start to draw it, slightly below this, but clearly much higher than that. And again, we're going to start right with the front carbon always being the same. And then the back carbon, we've gotten to an eclipsed conformation again. And the methyl group on the back ended up here. Okay, and we can label this as our 120 degree position. And we're just going to keep going. And let's think about now, once we reach a staggered conformation again, it's going to have the two methyls anti one another, which is sterically the best possible to get them as far away from each other as possible. And it'll be lower in energy than when they are gauche. So we're going to draw our next conformation just a little bit lower than the gauche conformation. And again, it's going to be staggered. And our methyl groups will be anti one another. And that's the lowest energy conformation for butane. I'll label that 180 degrees. Right? And then we just keep going. If we're rotating, again, the back carbon clockwise, we'll end up with a similar energy Gibbs conformation to the one at 120 degrees. So I'll go ahead and draw in, try to draw it at the same energy level here. Oh, again, messed up. Trying to draw it staggered when it should be ellipsed. It's good to draw it in pencil so you have an eraser. That's okay. So again, that back methyl from here will end up behind the front hydrogen. And this is 240 degrees. So if we go back and do another 60-degree rotation, they'll end up gauche again. Right? So we should try to hit the same energy level as we did for the first gauche conformation. So the methyls are here and here, and all the rest hydrogen. And again, they are gauche. Degrees. And then coming back up here, if we rotate for the full 360 degrees, they'll end up at the same position they were at 0 degrees because we've just done a full circle rotation. So I'm going to try to hit the same energy level as I did for the first one. And then I can literally just copy what I have at 0. Okay, so, and then let's think about the energy differences here, right? We have the lowest energy conformation here. So this will bottom out at 0 on our relative energy scale, right? And then the gauche conformations were 3.8 kilojoules per mole higher than the lowest energy anti-conformation. And so that is going to be at about 0.91. Right, so this would be 0.91 kilocalories per mole, 0. And then the highest energy conformation was 19 kilojoules per mole higher than the lowest energy conformation. And so that's about 4.5 kilocalories per mole. Right, and then these two were 16 kilojoules per mole higher, which is about 3.82. So that should give us a good idea of how to go ahead and put in energy levels on our graph here. It'll be hard to see everything all together. That's okay. Just focus on the graph for now. Okay, so again, we're going to try to estimate those energy levels, right? So we talked about the 0 degrees, the highest is about 4.5. I have that in there. And then at 60 degrees, it was 0.91. My best to estimate that. Up to 3.82. I'm doing my best to estimate that. Down to 0, relatively speaking. Back up to 3.82. Down to 0.91. Then up to the highest 4.5. Okay, and then we can sort of work on connecting those in a way the best of our artistic ability. Something like that. Okay. And we're just stop. And then if we wanted to come back and label, right, everything we had done before, we can do that. We can just say this is A, B, C, etc. And then here, this is A, B, C, way to G. Okay. Moving on then to the last page of the activity. It wants us to just practice drawing Newman projections. Wow, compared to what we did last, this seems like it should be more straightforward, which is great. Okay, so this is showing you the perspective of how you should be, looking down the carbon 1 to carbon 2 bond, right? And pointed straight down, we have 1, right? And then sort of off and to our right is 2, 3 being off and to our left from our perspective. And again, if you're really having trouble seeing this, I really encourage you to make a model using your model kit and get everything in the right way so that you're looking down the bond appropriately. And then hopefully it will help you really visualize what it looks like in 2D compared to a 3D model. From here on the back carbon, we've got carbon 6 pointing straight up, right? And then sort of coming out into our right is 4. Back into our left is 5. Okay, moving on to the next one. Right? Now we're looking up this carbon-carbon bond. So that means if this is the front carbon represented by the dot, and this carbon is the back carbon represented by the circle. So on the front carbon pointed straight up, we have group number 6, right? And now from our perspective, right, coming the number 4, which is on a wedge, is coming pointed down and a little bit to our left. Right, so this would be 4, 5. And then on the back carbon, 1 is pointed straight down, right? And you can think of it as like both 2 and 4 are on the same side, right? Because they're both on a wedge, they're both sort of to the left. So that should be on the same side. So 2 should be on the same side as 4. That could be one thing that also helps you notice those are on the same side, so they should be on the same side on the Newman projection as well. And then 3 and 5 are on the same side. So that might be something that could help you if you're struggling with this. Looking up this carbon-carbon bond here, the 1 is pointed straight up, right? And then our 2 off and to the right, and 3 is back and to the left. And then 6 is completely opposite 1, right? Pointed straight down. And then again, you can think of 2 is on the same side as 4, right? So we should put the 4 on the same side as 2, and then 5 is behind. same side as 3. Okay, moving on. Now we're looking down, right? This carbon-carbon bond, which makes this carbon 1 and in the front. That makes this 6, right? Pointed straight down. And then coming out of the page and to our left is 4. Going back into the page and to our right is 5. 1 is opposite 6, pointed straight up, right? And then 2 and 3 here. Right now, it's sort of transitioning to actual groups. These are just methyl groups where they haven't drawn in the CH3, but that's okay. We can add those ourselves, right? If you want to, you can just say, okay, this is CH3. Remember that in a line structure, that's often left off, but you know that it's there and you can add it in if you want to. We're going to draw a Newman projection, right? And from our perspective, we're looking down this bond. So the methyl is pointed straight down. And then the hydrogen is to the left and back. And the chlorine coming out of the page and up and to the right. And then the methyl on the back carbon is opposite the methyl on the front carbon. So it's up. Right? And then we have our groups to the left and the right. And then again, from this person's perspective, the hydrogen would be off to the right and the chlorine would be off and down to the left. Okay. So let's do the next one. Now we're looking up this carbon-carbon bond. Okay, and as we're doing so, we see a chlorine pointed straight up. Right, and then from our perspective, this hydrogen is coming out of the page to our left. And then the methyl is down and to the right. And on the back carbon, there's an OH group pointed straight down. And there is a, right behind this methyl group, right, sort of to the right is a hydrogen. Right? And on the same side as this hydrogen is this methyl group. Okay, we'll keep going here. Draw another circle with a dot. We are looking up this carbon-carbon bond and pointed straight up is a bromine. Right, and then coming out of the page and to our right is hydrogen. And into the page and to the left is a methyl. And then looking down here, I have a methyl group on the back carbon pointed straight down. And then I also have a fluorine off up and to my right. And a methyl group up and to my left. Last one, now we're looking down this carbon-carbon bond. And we have the methyl group pointed straight down on the front carbon, which is this one. Right? And then we have the hydroxyl group pointing out of the page to our left and the hydrogen pointing back into our right from this person's perspective, right? And then on the back carbon, we've got the OH group pointed straight up. Right? And from this person's perspective, the hydrogen group would be coming out of the page right into their left. The methyl group would be that. Okay, so hopefully you guys are able to see this. Again, model kits are great if you are struggling with visualizing this. I hope you have a great evening.